Hi class. In the last video we took a look at what happens to a parcel of air as it ascends, but we all know whatever goes up must come down. And so let's take a look at what happens to air as it descends. So let's draw another parcel of air. Okay. And we're going to cause this air to descend, come back down towards the Earth's surface. Okay, let's assume that we've got, again, 10 molecules of air in this parcel. 4, 5, 6, 7, 8, 9, 10. Okay, and we're getting this air to descend. Perhaps it is coming over a mountain, and now it's going to come back down the lee side of a mountain towards the surface. So again, the first step is that the air descends. Okay, when the air descends, now as it comes down, there are now more air molecules above this air parcel. And with more air molecules above it, that means that the pressure on this parcel of air is going to increase. So the pressure is going to increase. Okay. As a result of the pressure increasing, now you're putting more pressure on it, so that air parcel is going to compress. So the air compresses. Okay, and so down here, when the air compresses, our air parcel will be smaller. Okay, and those 10 air molecules are going to have less volume now, 5, 6, 7, 8, 9, 10. Less volume to it, so those air molecules are going, those 10 air molecules in our air parcel are going to be closer together, and so the density of the air is going to increase. Okay, if the density of the air is increasing, the molecules are closer together, they're bumping into one another more frequently, creating friction, and so our temperature is going to increase. Okay. So once again, if we relate this back to humidity, we look at relative humidity is equal to the mixing ratio divided by the saturation mixing ratio. If we assume that the mixing ratio is not changing, then we look at the saturation mixing ratio. If our temperature is increasing, okay, that means our saturation mixing ratio is increasing. Saturation mixing ratio being in the denominator means that the overall number, in this case the relative humidity, is going to decrease. Okay, so as the temperature increases, the saturation mixing ratio increases, and therefore the relative humidity is going to decrease. Okay, and if we bring it all the way down to the Earth's surface, okay, so once again, all those steps are in place. So the air descends. Okay, there are more air molecules in the column of air pressing down on the air parcel, so the pressure is going to continue to increase as it continues down towards the surface. Okay, as the pressure increases, that's going to act to compress that air parcel. The air compresses. When you compress the air, now that air parcel is going to be smaller. Still going to contain 10 molecules of air. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and so now those 10 air molecules are in a smaller volume, so the density is going to increase. When the density increases, the temperature is going to increase. Okay. And again, when the temperature increases, saturation mixing ratio is dependent on air temperature. As the temperature increases, the amount of water vapor the air could hold increases, so our saturation mixing ratio is going to increase. Saturation mixing ratio is in the denominator. So if the denominator is increasing, the overall number, which is the relative humidity, is going to decrease. Okay. So a good practical example of this is if you've ever noticed the leeward side of mountains, okay, in the United States, well, I guess everywhere, well, in the United States, we'll stick with that. The leeward side of mountains, it tends to be brown and pretty barren, tumbleweeds blowing around, and that's because as the air descends down the side of a mountain, all of these steps are in place. The air descends, the pressure increases, the air compresses, the density increases, the temperature increases, saturation mixing ratio increases, relative humidity decreases. So you typically get less moisture on the leeward side of mountains than on the windward side of the mountains. A good example in Washington State, Seattle, Washington, which is on the windward side of the mountains, air coming off the Pacific. Seattle has an average annual precipitation of about 80 inches of rain per year. But if you go on the leeward side of the Cascades, like in Spokane, Washington, so that's in the eastern part of Washington State, you've got air coming down off the mountains, off the Cascades. All of these processes are in place. Spokane has an average annual precipitation of about 16 inches per year. Okay, so things are much drier on the leeward side of mountains and much wetter on the windward side of mountains. Okay, so hopefully that makes sense to you, and let me know if you've got any questions.